Welcome back to Honors Calculus. In this video, I would like to finish up our discussion of continuity on an interval by looking at the idea of differentiability. In the last video, we took a bit of a tangent. I've gone blurry again. Let's try one more time to get that to be unblurry. I think that's a little bit better. It's not perfect. Right. In the last video, we looked at the idea of the derivative of a function and the differential operator. And I said that we would use that, and it was a more powerful condition than continuity. And that's one of the things that I want to take a close look at here in this video. So let me get my blurry head out of the way, and let's take a look. All right. We say that a function is differentiable at a point C if and only if the derivative f prime at C exists. And we say that it's differentiable on an interval from A to B if and only if it's differentiable at every point in that interval. You can also define the left side and right side derivatives to get differentiability at a closed interval. For our purposes this semester, that's not something that's going to be useful, so we're not going to try. It does exist. You can take a one-sided limit of the derivative of the difference quotient and go from there. It doesn't help us anything in what we're doing this semester, so let's leave that lie for now. Let's write the right thing down. And my theorem tells us that if a function is differentiable on an interval from A to B, then it is also continuous on that interval. As I said, differentiable is a more powerful condition than continuity. All right, to prove this, let's pick a point C. And we know that the definition of the derivative, we have a couple of versions of it. I'm going to, at this point, go back to the limit as x approaches C version because I do know the particular value where I want to do things. When you know the particular value, the limit as x approaches C version tends to be a little bit easier to deal with. Right, we know that this limit exists. So what I want to do is take a different limit and play around with this. Let's consider the limit as x approaches c of f of x minus f of c. I could approach this in two very different ways. There is the straightforward way, where I split the limit up over the subtraction, and I get that the limit of as x approaches c of f of x minus f of c is the limit as x approaches c of f of x minus the limit as x approaches c of f of c. Now for the first one, I don't yet know that the function is continuous, so I don't know for certain what the limit as x approaches c of f of x is. But I do know that f of c is constant with respect to x, so this limit is just the value of the constant. All right, that doesn't seem like it does much of anything. But now let's do something silly. Going back to the same starting point, the limit as x approaches c of f of x minus f of c. I'm going to do mathematicians' second favorite thing. Mathematicians' favorite thing is to add and subtract the same thing and pretend that nothing happened. Mathematicians' second favorite thing is to multiply and divide the same thing and pretend that nothing happened. Right? The limit as x approaches c of x minus c times f of x minus f of c all over x minus c. Assuming that these two limits exist, we can split this up over the multiplication and separately look at the limit as x approaches c of x minus c and look at the limit as x approaches c of f of x minus f of c all over x minus c. And the limit as x approaches c of x minus c is going to be c minus c. And the limit as x approaches c of f of x minus f of c all over x minus c, that's the definition of the derivative. So that's f prime of c. And that gives me 0. All right, that's a long way to go to get nothing. But the key is I started at the same place, which means that where I ended up has to be the same place. The limit as x approaches c of f of x minus f of c must be equal to 0. And adding f of c to both sides of the equation gives me that the limit as x approaches c of f of x is equal to f of c, which is the definition of continuity. So f is definitely continuous at this point c. And since we just did that for an arbitrary point in the interval from a to b, it will work for all of them. Right. Of course, just because a function is continuous does not mean the function is differentiable, right? Differentiability is stronger. If the function is differentiable, it's continuous. If the function is continuous, it may or may not be differentiable. So consider the function. Actually, let's go with the function absolute value of x minus 2. Remember that absolute value is defined as a piecewise idea. F of x is equal to x minus 2 if x minus 2 is greater than or equal to 0, and f of x is equal to the opposite of x minus 2 if x minus 2 is less than 0. Right? Cleaning this up a little bit and putting it in terms that are closer to what we normally do, this is going to give me that f of x is 2 minus x if x is less than 2, and f of x is x minus 2 if x is greater than or equal to 2. You can see that the one place you'd have to worry about continuity for this function is when x is equal to 2. I encourage you to take the time to verify for yourself that this function is continuous. The limit as x approaches 2 of f of x is 0, which is exactly the value of f of 2. Right? I'm not going to show it, but I encourage you to take a look at that. But what of the derivative? F prime of 2. Well, we have a couple of ways of talking about the derivative. The limit as x approaches 2 of f of x minus f of 2 all over x minus 2 is a classic way of dealing with it. F of 2 is, of course, 0, but f of x changes value whether you approach from the left or from the right. So we have to separately consider the limit as x approaches 2 from the left, which would be as x approaches 2 from the left, the value of f is 2 minus x. And 2 minus x divided by x minus 2 is negative 1. And the limit as x approaches 2 of negative 1 is negative 1. But if we approach from the right, we get x minus 2 over x minus 2, which is positive 1. And the limit as x approaches 2 of positive 1 is positive 1. So the limits disagree with each other. We have a limit that does not exist at this point. Even though the function is continuous, it is not differentiable. There are a couple of ways that you can think about this. What I think of is that differentiability involves a certain amount of smoothness. If a function is differentiable at a point, the graph y equals f of x is smooth. For example, a parabola, y equals x squared, is smooth pretty well everywhere. Compare that to the absolute value. Absolute value of x minus 2 is this thing, which is pointy at the point x equals 2. Yes, that's a technical term. When the graph is pointy, it is not differentiable. When the graph is smooth, it is differentiable. Or better, as we put it in analytic geometry, we look for differentiability to show where the graph is smooth. By identifying the points where a function is not differentiable, we will identify the points on the graph that are not smooth. I have one last idea that I have to talk about in this video, and that idea is linearity. An operator in general is called linear if you take a linear combination, which is a times one thing, a times f of x, plus b times another function, b times g of x. If you apply that operator, you can ignore the addition, you can ignore the constants, and simply take the operator on the two functions. So if you want to take the derivative of a times f plus b times g, you end up with a times f prime plus b times g prime. The proof of this idea of linearity is given in the typed notes. I encourage you to take a look at it. There's some interesting things that come out of that. We will be using linearity in the rest of this course. That's one of the most powerful things about the derivative and about the other operator I've hinted at that we'll be talking about later on in this course. And some of the techniques we use in the proof will come up again next week. So I encourage you to take a look at that. But I'm running low on time, so I'm not going to go through the proof in this video. Instead, I would like you to determine where the function is continuous and or differentiable. Let's take a look at f of x is equal to x if x is less than or equal to 1, and f of x is equal to x squared if x is greater than 1. Determine where the function is continuous and or differentiable. Where it's continuous, where it's differentiable, where it's both, where it's one but not the other, where it's neither. Take a few minutes, play around with that idea, see what you come up with, and I'll see you in the next lesson.